again, people to share with. So I was asked to put together a presentation that gives a little bit of background on the Kentucky Climate Center, a little bit of history of what we are, what we do, and then the main focus is just looking at climate data for Kentucky and just trying to look back through the record, the objective data that we have, and interpret that in terms of what kinds of trends and patterns we see. And much of this is based on the technical report that I drafted this past summer, and based on use of some data visualization methods and so forth. What I did not do was include slides that talk about what climate change, what the driver is, or drivers are, and sort of some of the standard graphics and so forth about how greenhouse gas concentrations have been increasing and that sort of thing. I figured that's stuff that most people are familiar with and didn't want to cut in too much on my time. But having said that, there, as you all know in this group, a big part of communication of climate change is beyond just the data, is talking about the nature of the issue, the politicization of the issue and so forth, and trying to find a way to find common ground with people. But I didn't think that I needed to go down that route today. So the Kentucky Climate Center was created in 1979 by my predecessor, Glenn Connor, who unfortunately passed away early this year. And he had served as state climatologist from 1978 until 2000 when I succeeded him, and he was a wonderful mentor to me. Prior to 1973, the state climatologist position was affiliated with the National Weather Service. So it was a position, and then during a period of budget cutting, those positions were eliminated from the federal budget, and various states picked up that role at different times. So in some cases, like Kentucky, there was a short gap where there was no state climatologist, but again, that didn't last too long. So with the creation of the Climate Center in '79, we became ARSCO designated. That's the American Association of State Climatologists recognized state climate office in 2002. And that was part of what at that time was referred to as the National Climate Services Partnership. The state climatologists were affiliated with the, at that time, the National Center for Climatic Data, and since then that's been changed to the National Centers for Environmental Information. So have that affiliation at the federal level, and then with the National Weather Service offices that serve Kentucky, and the Midwestern Regional Climate Center, which is located at the University of Illinois in Champaign. Actually, those contracts, I think, are currently up for renewal or bid, so I assume it's going to remain there, but it could get relocated somewhere else, I guess, when they make the announcements. So we are also affiliated, work closely with the National Integrated Drought Information System, in particular through their Midwest Drought Early Warning System. We work with the USDA Climate Hubs. We're technically in the Southeast, but we actually work more with the Climate Hub in the Midwest at Iowa State University. We've worked closely with NRCS, and they've been a really good partner with us here with the Kentucky Mesonet. And we're in the process of trying to formalize a partnership with the U.S. Forest Service Office of Sustainability and Climate and the Daniel Boone National Forest here in Kentucky. So the Climate Center, what I try to tell administrators here at the university, because it's an ongoing challenge, is that we're unlike many centers which are kind of created at the grassroots level. We're part of a strong national network with lots of affiliations at the regional and national level. And those are really important because they, again, create these networks of people and experts that you can tap into. If you're not familiar with the National Centers for Environmental Information, or particularly with the Midwestern Regional Climate Center, I would encourage you to check out those folks. And the Midwestern Regional Climate Center has an excellent website and database and lots of resources. And the information I'm presenting today, really most of it comes through the Midwestern Regional Climate Center. So if we look back at the history of record keeping in Kentucky, the first climate observations were taken in July of 1825 at the Newport Barracks. If any of you have been up to Cincinnati to go to a baseball game, you could stand at the stadium and look across back to Kentucky, where the Licking River comes into the Ohio River, and that's where the Newport Barracks was located. So at that time, it was the U.S. Army surgeon that was assigned to the barracks there in Newport, who was given the responsibility of recording weather observations on a daily basis. And that was because at that time there was, as we were settling into the interior of the country, there was very little information and knowledge about the climate, and there was concern about the effect of weather and climate on the health of soldiers and population in the country. So that was what motivated that effort. So we have some records that go back that far. The sad thing is that some of those records were lost. Ironically, they were concerned about the possibility of losing those records as a result of flooding, which occurred periodically there on the Ohio River. And so they had decided to, transfer the historical records after they'd been collected for a while off of the barracks to a more secure location, but they were lost in the process. Anyway, that's the earliest record. And then there were a few periods in other stations in the 1800s where there were observations collected. We certainly don't have a detailed record of climate observations through that century, but we do have some data from random kind of locations across Kentucky for various periods during the 1800s. You can see how the responsibility for record keeping changed through that time, from the U.S. Army to the Smithsonian Institute, the U.S. Army Signal Corps, the U.S. Department of Agriculture. That's when we really started to see a growth in the number of observing sites across the state. And then with the rise of aviation, that was transferred to the Department of Commerce, and we saw the location of stations at the airports and such. And then in 2007, with the funding through the National Weather Service for the Kentucky Climate Center's effort to build the Kentucky Mesonet, that system is now recognized at the state level as our official source of climatological observations. So on the bottom, you can see a picture of a cooperative observer, part of the old National Weather Service program. People were, again, volunteers, or in some cases maybe got $25 a month or something of that nature to go out and collect a daily observation for the high and low temperature and the amount of precipitation that fell. And then in the late 1900s, 1990s, I believe, we started to see the rise of technology and the development of these so-called automated temperature systems, MMTS units. And there's a picture of one of those in Russellville, Kentucky, The gentleman on the left, who's now deceased, by the way, was from Summershade, Kentucky, down in Metcalfe County. It's one of my favorite place names. The idea of having an address in Summershade seems to be just a wonderful place to live. And then again on the right is a picture of one of our Mesonet stations. So with that, that's a little bit of background on the Climate Center and our observations from the state. So I wanted to get into a little bit of trivia, so to speak, but looking at some of our records and extreme temperatures and such, but not just for the trivial perspective of it, but also to kind of prime the pump for a little more detailed discussion of climate trends here going forward. So our highest temperature ever recorded in Kentucky, 114 degrees on July 28, 1930 in Greensburg, Kentucky. They're in Greene County. So that was the high temperature by 1 degree. There was, I think in Bowling Green, 113 degrees recorded, and there were numerous days that summer with temperatures above 100 degrees. So Lovelessville over in Ballard County, I believe it is, totaled 30 days that summer with temperatures reaching 100 degrees or above. So one thing to note there is the year. So when we look at climate change and the concerns about increasing temperatures, one might expect that our high temperature records would be more recent, but most of our high temperature records go way, way back here in Kentucky. Low temperature wise, our record low temperature, I actually remember this one, minus 37 degrees on January 19th, 1994. I don't know how many of you were here in Kentucky at that time. I remember that event. It was we had a blizzard that included ice, freezing rain, ice accumulation, snow on top of that, numerous power outages. The interstate highway system was shut down for upwards of a week. And on the back side of that system, as it went through, then you had clear skies, snow cover, and extremely cold temperatures. So that record was set in Shelbyville, down in the bottom of a narrow ravine. So it's actually not a good place to be measuring temperatures to get a representative temperature measurement, but it was a perfect place to catch an extremely low temperature. And then if you go back to the winter of 1917 and 18, we had 24 mornings in Farmers, Kentucky, over near Moorhead area, 24 mornings with temperatures below zero. So that's a record that I personally have no interest in seeing broken again, and probably very unlikely given climate trends. So beyond temperatures, we look at extremes of precipitation, and instead of just looking at amounts, probably the way that precipitation extremes get expressed is more in terms of flooding, flood events. And so in Kentucky, we think of the Great Flood of January 1937 on the Ohio River and its tributaries. That month, the statewide average precipitation was 15.77 inches, and some locations, again, recorded over 22 inches of precipitation during that month. Most of that was rain, some of it was snow and sleet and such, but it contributed to record flooding in our cities along the Ohio River. Of course, that's prior to the development of the systems of locks and dams on the Ohio River and its tributaries. And likewise, in eastern Kentucky, we were devastated by flooding on numerous occasions, and it was not a good sign for a year that ended in 7. With major flood events in 27, 37, 57, 77, and 97. And again, we've continued to have significant flooding events. One that stands out to me was 2011, when we had flooding in the springtime with water running through the spillways of some of our Army Corps projects. which is something that I never ever imagined I would ever see happen. In addition to extreme precipitation, we have extreme drought. And again, now we go back to that 1930 period in Greensburg where we had the record high temperature. And that summer where they had 19 days of 100 degrees or higher along with that record temperature, they went for a period of 47 days with a total precipitation of less than 1 inch. So that was a really hot, dry summer. And statewide, our average precipitation for the year was just under 30 inches compared to average statewide, which would be closer to 50 inches, a little bit less than that, about 48, I think. So let's take a look back now at factors that influence our climate here in Kentucky. And it's a bit of a simplification, but I think that's appropriate in terms of providing context for how we think about climate. So we have kind of three fundamental things that influence our climate. You know, we could probably add some other things in there, but again, so trying to simplify things instead of becoming too complicated. So one thing that influences us is that to the extent that Kentucky is sort of interior to the country, away from the coast, then interior regions are typically drier, and the farther you are away from the oceans, you tend to be prone to more extremes of very hot temperatures in the summer and very cold temperatures in the winter. So, you know, we are affected somewhat by that continental influence. We're certainly not, don't have the same continentality as North Dakota or South Dakota would have, but nonetheless, we are certainly not a coastal state. We're located north of the Gulf of Mexico, and our prevailing winds are from the south, and so that leads to the advection of moist tropical air, bringing humidity into our region and being the source of much of our precipitation, especially in the summer season. And then we're also kind of in the mid-latitudes where we are influenced by the storm track associated with the jet stream that generally runs west to east, but can modulate quite a bit in terms of the actual direction, in terms of troughs and ridges and troughs that kind of create a bit of a roller coaster across the country in the movement of those weather systems. And so to the north of the jet stream, it tends to be cooler and drier. To the south, it tends to be warmer and moister. During the summer season, that jet stream tends to migrate to the north. And again, we become very humid. We have very few frontal systems that affect us in the summertime compared to the winter season. In the winter, the storm track drops farther south. And again, we get more active weather patterns that typically move across the state. That position of the jet stream is affected by the so-called teleconnections, including things like the El Nino and La Nina circulations. And we're in a La Nina circulation this winter that's supposed to affect what our climate looks like through the coming months. So all of those things serve to affect our climate and contribute to a very high degree of variability in our climatic conditions from year to year. Certainly more variability here in Kentucky than what you might have near the equator or in, along the West Coast and places like that. So moving on, we know a little bit about some of the drivers of climate. Then the next question relates to, you know, kind of recognizing climate change if you saw it. So when I was younger, I used to go deer hunting. My father grew up in the hills of West Virginia and loved to go out in the woods and hunt. And he taught me to do that when I was young. It's been many, many years ago since I went deer hunting. But one thing I learned early on is if you're going to go deer hunting, it helps to know what a deer looks like. And so the same could be said about climate change. If you're looking for climate change, you know, how would you recognize it if you saw it? It's not easy, especially in an area like Kentucky, again, where there's just a very high degree of natural variability in our climate. And you can see that pretty easily. We go back just a few years. In 2010, some of you may remember a storm system that came through the 1st of May that dropped copious amounts of rainfall. It was even more devastating in Tennessee in the Nashville area. But here in Bowling Green, we had over 10 inches of rain at one of our Mesonet stations within 36 hours and contributed to extreme flooding and water showing up in places that was never expected to see it. And then later that year in October, there's a picture on the bottom row there from Todd County. And so that's about, 50 or 60 miles as the crow flies from here in Bowling Green. And if I didn't tell you that picture was taken in Todd County, you might think that was taken out somewhere in Colorado or Nevada or Utah, something like that, in a much more arid climate, but not the case. So we went from extreme precipitation and flooding into drought. And then the next spring in 2011, I mentioned earlier about the flooding on the lower Ohio River and many of the Army Corps projects. This was the reservoir, Rough River Reservoir in Grayson County. And again, there was water going through the spillway. I have a couple pictures of that. I didn't include that here. And then the next year, and by July of 2012, we were in an exceptional drought period that really devastated, the corn crop for most farmers across Kentucky, where corn yields averaged somewhere about 65 or so bushels per acre, about a third of what they might normally be. So, there's just a tremendous amount of variability. Do each of those events represent climate change or not? So now let's start taking a look at, again, some more historical statistics, and we'll start out with some tables, but we'll then move into looking at some graphs. So the 10 most extreme years in Kentucky precipitation-wise. So we've got the 5 wettest and the 5 driest. And one thing that stands out there on the wettest years is that 3 of the 5 wettest years have occurred within the last decade. So that's a pretty remarkable thing right there. And if you look at the driest years, the most recent year that's among the 5 driest years, we have to go all the way back to 1963. So that really kind of stands out if you're kind of measuring, weighing the scales of justice. It really looks like there's some extra weight on the increased precipitation side of things. And again, we'll look at that more here. So this is a graph that came out of the technical report that I released, and it plots, again, statewide average precipitation on an annual basis. And let me explain a little bit about everything you're looking at. So each of the dots there is a different year on the horizontal axis, and the vertical axis, of course, is the average precipitation total. The solid line that kind of follows the data is a smoothing curve that it's kind of like a regression line, but it's not required to be a straight line. It's has the flexibility to kind of follow the data, but nonetheless, like a regression line, it's essentially trying to track how the average statewide precipitation is increasing or decreasing, as the case might be, across the state. And you can see with that line that it shows a clear increasing trend, especially over the last few decades. The rectangles on the graph, you can see each, looks kind of like box plots if you're familiar with those. So for each decade, defined as, for example, 1900 through 1909, I took those 10 years, and the darker shaded rectangle represents the middle 60% of those years, and the lighter shaded green captures on the upper side, the two wettest years out of those 10, and on the bottom side, the two driest years. So that, again, kind of tracks how the, what I call the middle majority of the years, how that's trending compared to others. So from looking at that, again, it's very clear that our precipitation amounts have been increasing. I mentioned that we've had 3 of the 5 wettest years within the last 10 years, within the last decade, and those are circled there in the upper right. But interestingly, if you go back, I asked the question, you know, have we ever encountered anything like that before, where we had 3 extremely wet years, you know, in a very short period of time? And it turns out that it had happened before. Back during the 1950s, at that time, I circled those years. Those were, at that time, 3 of the 5 wettest years we'd ever recorded in the 1950s. And then again in the 1970s, we had 3 of the 5 wettest years through the 1970s that occurred within that period. And then now we've broken that record once again. So the takeaway there, I think, is that with the amount of variability that we have in our climate, we are going to have some wet years and we're going to have some drier years, but the trend has been upward, and the extremes keep getting higher and higher every few decades. So to me, that's a pretty compelling case that our precipitation patterns are increasing. We're getting wetter here in Kentucky. This is a similar type of graphic, but it's broken down for overlapping 3-month seasonal windows. So in the upper left, you see December, January, and February. So that's the winter season per se. And then we drop off the December and add the March. And so we have January, February, March in the second panel on the top row, and so forth. So it's overlapping 3-month segments. So it kind of smooths out the pattern a little bit. So there's a lot in there, so I'm not going to try to go through every detail, but I did highlight there the April, May, June, July windows that show the strongest pattern in terms of increasing precipitation. So our precipitation has increased statewide over the course of a year, but it's particularly been noticeable in the spring seasons there, April, May, June, July. Having said that, if you look across at each one of those, you can see each seasonal window is showing at least a slight upward trend in precipitation, but still, again, you should be struck by the amount of variability from year to year. So that variability makes it really hard for the average person to say, well, gee, the climate's changing. I can tell, I can see it. It's difficult because there's so much variability. And now it looked at the same data, but pulled that out for just looking at the growing season. So this is April through September. And so I put this in here because its significance to agriculture. And again, it's pretty remarkable, actually, that you see that if you look at the smoothing curve, that average precipitation in the first half of the 1900s was somewhere in the 22, 23 inch range. And now it is up more in the 26, 27, even 28 inch range. So that's a fairly significant increase in average precipitation in the growing season. So moving to temperature, our 10 most extreme years in Kentucky average temperature-wise, our 5 warmest years, you can see 2012, 2016, 2017, 3 of the 5 warmest years within the last decade. The coolest years, the most recent cold year, 1979, and you can see the late 1970s. Again, some of you may remember that period. I certainly do, where we had some extraordinarily cold winters and blizzards and a lot of snow cover for many, many days. Again, it's been a long time since we've had a particularly cold year in Kentucky. So this is the average trend for annual temperature. So this is averaging everything through all the months of the year. In some ways, not the most useful thing to do because you're lumping the winters with the summers and such. But in terms of getting a composite view, this is what it looks like. And it's kind of like a roller coaster. We had a very warm period in the first half of the 1900s, and you can see an extreme year, 1921, our warmest year on record. And then things got cooler through the 1960s and 70s before warming again. And you can see that the upward trend is such that on average, we are now warmer than we were in any prior period. However, we have not broken the record for the warmest year going back to 1921. But again, this is lumping all months of the year together, and that's a little bit deceiving. So the pattern here in Kentucky is a little complicated. There's research that has identified something that's been labeled the warming hole, the United States warming hole. And this is an area you see on the map where, in spite of increasing temperatures across the country and the continent, these areas have tended to be cooler than others. And so we saw that big dip in temperatures. That's characteristic of the Southeast and parts of the Midwest. So the Southeast tends to have more of a cooling signature in the winter months. In the Midwest, it's more of the summer season, but for Kentucky, it's both. So again, we stand out. When I talk to people about climate change in Kentucky, basically the message is if you're hearing about climate change and you're convinced that, gee, it's warmer than it's ever been, this is incredible. It's not in Kentucky because we're just kind of getting back to where it used to be because of this warming hole in our region of the world. So let's break that down now by season. And if we look at extreme summer temperatures, our warmest summers, there's 2010, but otherwise 1952, 1943, 1936, 1934, with the one exception there, those are all from now, close to a century ago. Whereas if we look at the coolest summers, again, we don't have any particularly recent ones, 1992. Bottom line is summer temperatures in Kentucky, there's nothing that really stands out that suggests that, gee, summers are becoming just unbearably hot. It just doesn't show up that way in the data. This is the same set of graphs that looks at trends for those 3-month seasonal windows. And a couple things I'll point out here. One, I've got some of those summer seasonal windows highlighted because those are areas where, again, you see that warm period in the first half of the 1900s and then a cooling period, and then we've started to warm up again. But the average summertime maximum temperatures are still well below where they stood back in the first half of the 1900s during the summer season. But if you look at the winter season, other times of the year, the average high temperatures are now as high or higher than they were historically. You can also notice there a little bit that the variability of the high temperatures tends to be greater in the cool seasons of the year than during the summertime. And that will become even more apparent here when we look at low temperatures. So here's our seasonal windows for minimum temperatures. Now we're looking at the average daily low temperatures. Notice in the summer seasons just how much lower the variability is the patterns are a little bit more clearly defined, and you can see the very seasonal. I highlighted some of those, but probably really should highlight the entire middle row there, where you can see that the average low temperatures from April, May, June, all the way through July, August, September are all higher now than they were historically at other periods. But again, the variability from year to year is much lower in the summer seasons than it is in the winter seasons, where the variability tends to be quite high. So, but that middle row is interesting, because when we looked at the high temperatures are warming, but they have not caught up with where they used to be. Whereas the low temperatures are warming and they've already surpassed what they used to be. So the fact that we're looking at different patterns in the highs and the lows suggests that we might want to take a look at what we call the diurnal temperature range, the difference between the daily high and the daily low temperature. So this is a set of graphs, same seasonal windows, and is looking at the relationship between the diurnal temperature range and the amount of precipitation. And you can see that during the winter months, December, January, February, and then down at the bottom right, November, December, January, there's really no particular pattern. But as you get into the warm season of the year, there's a very strong negative relationship that shows that when it gets wetter, the diurnal temperature range gets smaller. And that's important because we've seen with the increase in precipitation that our low temperatures have been going up, our high temperatures haven't been going up as much. That's consistent then with the idea of our increasing precipitation. So our diurnal temperature range trends in the state show that during the summer seasons, where diurnal temperature range is very sensitive to precipitation, that increase in precipitation is leading to a lower diurnal temperature range. And again, focus on that middle row there, where the smoothing curve tends to show a pretty clearly defined downward trend across those windows. Not as evident during the cool season of the year, where the relationship between diurnal temperature range and precipitation does not exist. So getting near the end, these are graphs that are essentially heat maps. And what I did here is I ranked the data for each month of the year. So if you look at, for example, the top graphic there, and look at the bottom row for January, I took all of the January precipitation data and I ranked them from the wettest to the driest Januaries. And then I plotted them with different color coding and did that for each of the other months. So there you can let your eyes detect what patterns you see there. So the darker shaded blues indicate wetter patterns. And based on what we talked about, it should be that the area to the right shows up, especially recently, as darker blue being more prevalent. But we've also talked about how much natural variability there is. And so it's still quite a bit of a mosaic of colors there that highlight that tremendous variability. And the lower right, the diurnal temperature range, the decreasing diurnal temperature range, fairly evident there, as you can see the more prevalence of the blue shading, especially during the warm season months over the last few decades, especially compared to the early 1900s, when we had more frequent drought and more extreme heat during that time. And then this last set is looking at the same type of thing, but for maximum temperatures and for minimum temperatures. So again, I'll focus more on the minimum temperatures. That you can see that as you move to the right side, there's a little more prevalence of reds. And again, especially in the warmer months of the year, but not every single year. to where we've tended to see an increase in our minimum temperature. So that basically means in the summertime, we're getting more of those muggy nights where the temperature, struggles to get down below 70 to where you can actually sit out and enjoy the evening outside. So anyway, that's those graphs are, again, kind of meant for you to be able to kind of let your eyes tell you what you see in terms of patterns across the state. Bottom line is Kentucky's climate is very complex. There's a high degree of variability, but it is clear that we are becoming wetter, and that increased wetness is a driver in the decrease in the average diurnal temperature range, especially during the warm season. And while the average temperature is increasing, the minimum temperature is increasing faster than average maximum temperature. And when you put all that together, you can certainly say that our climate today is very different than what it has been in the past. So with that, Kegel, I'll send it back to you, and if there are questions, comments, we can take some time with that.
Yeah, definitely. Thank you, Stu. Yes, I see Ellen does the reaction. By all means, y'all feel free to react appropriately to this great talk. This is exactly what I wanted. I feel like I have a lot more knowledge now than I did 40 minutes ago. We're gonna run a little past our agenda time because I ate into Stu's talk time with my director's report. So we'll go for about 10 minutes on Q&A, and then take a 10-minute break before we come back and do sort of organizational stuff. We already have a question in the chat, and I have the same question, Stu, and I also have a follow-up if nobody else has anything in the meantime. And actually, do you want to stop sharing, Stu, and that way we can see people bigger? Yeah. So Avery from University of Louisville asked, any hypotheses about what's causing the warming hole and whether we will revert to the wider mean, and if so, all at once. And I was similarly curious about the warming hole. I had not heard of this before, so I'm a little curious if, is that just because I'm like not a scientist and not a meteorologist? Is this something that's sort of commonly known? Is this a newer awareness? Like, where does that come from?
Yeah, I don't think it's super widely known. There is a little bit of literature on it. So I think it's getting a little bit more attention. There's there've been different explanations for it. I've heard some reference to changes in the amounts of aerosols in the atmosphere and such. I've also seen it tied to broader, longer-term cycles in terms of ocean temperatures and such. But to me, it's I think the key thing to me is that in many ways it's consistent with expectations of a changing climate, that as our oceans get warmer and the atmosphere gets warmer, there's more evaporation, more moisture in the atmosphere. And again, when you look at the relationships between precipitation and diurnal temperature range, it really shows a pretty clear connection there, which would explain the warm season component of the warming hole, but not necessarily the cold season portion of it.
I think you just answered my follow-up question, which was the causal relationship between the precipitation and diurnal temperature range.
Yes, and again, it's that's an important topic for us here in Kentucky from an applied perspective too, because what it basically says is that in our part of the country, where it's normally wet, when we get a drought that dries out the soil, removes moisture from the atmosphere, that extraction of moisture from the soil and from and the environment as such helps to create heat waves so that it can very much reinforce the development of drought. We really saw that, a great example of that last year when we had the flash drought in September, and we had temperatures well into the 90s, especially in the southern part of the state. I think we had Bowling Green, we had over 20 days in September with temperature of 90 degrees or above. So once the soil dries out, it enables the the clear skies and the sunshine to really heat the lower atmosphere.
Yeah, I remember that. I think Andrea might have been with me going to an orchard in October and, hoping for apple cider and instead getting sweat and
yeah, it was crazy.
Yeah. Yoko has a question in the chat as well. So my understanding, this is what she wrote. My understanding is that farming requires certain conditions to take place at expected times during the year. Are there any measures that would capture this happening or not happening? So I think that's a good follow-up to your point about the importance of this in terms of applied science.
Yeah. Again, that's beyond my area of expertise. So that's where I enjoyed tag teaming with Dave Van Sanford there when we had the other meeting. But it's certainly true that the timing of extreme weather conditions is really critical on the agricultural side. So a great example of that was the 2012 drought and heat wave, where the extreme heat coincided with the tasseling period for corn and germination, and it was just a worst case scenario, and things of coming together at the worst possible timing. So there's always that concern, and I know there was some discussion this year as to what's the possibility of something like that on a smaller scale happening, and it didn't really materialize per se. The other thing going forward, other concerns from a climate change perspective would be earlier in the year in terms of planting. If we start to see warmer conditions, wetter conditions in the spring, that can affect when farmers are able to plant. And, if it warms up, how soon are they willing to plant in terms of taking chances? So this year we had the freeze that negatively impacted the wheat crop and such. So the fact that we're getting warmer on average doesn't necessarily make it easier for farmers, because again, warmer on average is a change in the mean, but when we're looking at late season freezes, those are extremes that are not necessarily tied to an increase in the average temperature. So yeah, this is where we really need some of the agricultural experts that can kind of hone in and talk specifically from a crop perspective what's really critical. That there was on another side of that though, that I learned last few years. We had a couple winters recently, and I forget which one, the one in particular, where we had an extremely wet winter that was also extremely damp and cloudy and just dreary, and caused a lot of problems with livestock and cattle due to muddy conditions and the cattle getting wet coats and not being able to dry out. And there's a lot of fatality and such in the livestock.
Yeah, I think that might have been, it was the winter before Carmen and I were doing some water research, and we talked to folks about that. So in the sort of, I think 2017, 2018.
Yeah, I just don't remember, but yeah, that sounds reasonable.
Yeah. I know I was about to, Amanda, you anticipated me. I was going to say, we have a couple of ag specialists on the Zoom right now, and I didn't know if any of you wanted to pop in any specifics in terms of Yoko's question about measures capturing like applied observations for farming. Yeah, go ahead, Amanda.
I don't call myself a production expert by any means. Rebecca is much more versed in crop production than I am, I think. But so two different things I feel like we've talked about, one with cropping and also with livestock. And so one of the issues that, to follow up what Stu's commenting on about the issues with weather related complications in livestock, are thinking about that freeze thaw cycle in the soil, and we don't have those longer periods of frozen ground like we maybe have historically. And so when we get a lot of freeze thaw, and we have these muddy conditions, those are certainly contributing to water quality issues as well. And then challenges for farmers with winter feeding, not only with how it's going to impact the landscape and how they're going to tear their fields up, getting feed out and moving animals around and such, but, as Stu indicated, challenges with the overall health of the herd and what those temperature fluctuations and extremes might do to those animals. And in terms of cropping, some of the stuff I think about are in terms of conservation practices and how spring weather patterns influence what's happening ultimately with water quality. And so I threw in the chat there that a lot of my colleagues and I have conversations about, what is going on with fertilizer applications in the spring, especially in the Midwest. And some Midwestern farmers still put a lot of nitrogen on in the fall, and they just assume they're going to lose an incredible percent in my estimation. When I first learned about this, I'm like, how can you be okay with losing 40% of your nitrogen, even financially, just from a production standpoint? And not as many do that fall application of nitrogen, but some still do. Some still are putting poultry litter on as a nutrient source, and they're putting it on in the fall, and then they're losing that through the winter because we're not having a growing crop there. So these challenges with weather patterns and how that influences when farmers are getting into the field to plant, to do also herbicide or pesticide applications, those pre-emergent applications, plus when they're putting nitrogen on in terms of their planting. Those are all things that are contributing to water quality issues that, the folks that I work with on Gulf of Mexico issues, we're really trying to figure out how we encourage greater adoption of best management practices and conservation practices. So.
Thank you, Amanda. Yeah, this is why I love this group, right? Getting these different perspectives. It is so complex, these challenges. We have time for one more question for Stu, if anyone has anything in the chat or on mic. Okay, well, let's give Stu a round of Zoom applause, I guess. Feel free to unmic if you would like, or use an emoji. I appreciate this so much, Stu. Our sort of like inaugural keynote, if you will, mutual learning opportunity. This has been really wonderful. Again, I have recorded it. I'll stop recording in just a second so that we can share it to the members, and then Stu and I will talk about the possibility of sharing it more broadly in case you want to use it for teaching and such. We're going to break for 9 minutes and return at 2:20, at which point I'll give everyone a sort of update on organizational status and some cool things that are developing to help us do our work. So I'll see you all back at 2:20.